Hello, my name's Bruce Law. I'm a professor in the physics department at Kansas State University. I'm about to tell you about a model for dark energy, which is based upon the Born self-energy for the electron, which was recently published by me in this Astrophysics and Space Science in April of 2020. Here's a picture of how we think about the Big Bang and the universe's expansion. So here we have on the left the Big Bang, and of course we have the cosmic inflation in this point. Of course, we normally think of gravity as attractive, so that after the cosmic inflation, we get a deceleration in this region here. Here we can see where the cosmic microwave background is. Over to the far right is today. Of course, the object I'm talking about is this dark energy, where in fairly recent times, we see a repulsive gravity, which we think of as being caused by either the cosmological constant, lambda, or dark energy. Of course, one can measure as one goes from the Big Bang to today in various sorts of time scales. So here's a cosmic microwave background, which happened at a time scale of about 400,000 years after the Big Bang. Of course, today is about 13.8 billion years. We could alternatively measure this in terms of redshift. So the cosmic microwave background occurred at about 1100 redshift, and of course today's redshift is 0. Of course, we could also measure this length scale in terms of a scale factor A, which is 1 over 1 plus z. So this is the cosmic microwave background is about 10 to the minus 3, whereas today the scale factor is a value of 1. So what the scale factor means is that for sort of a length scale of 1 meter today, back at the time of the cosmic microwave background, that length scale would have shrunk to 1 millimeter. In other words, things would have been a lot denser back then. I'm going to blow up this region here around the point where we have dark energy. So here's this region from where we have dark energy. This graph is from Farouk in 2017. On the left, we have the Hubble parameter divided by 1 plus z. So this is actually a dot, the scale factor, the velocity of the scale factor, versus z. And the symbols are binned data. And the various lines are various theoretical models. So this here's the lambda CDM model in red fitted to the data. And one can see that close to z equals 0, we have an acceleration. In other words, the a dot is increasing with time. At larger z, larger than 1, whether we can see there was a deceleration. In other words, the a dot is decreasing with increasing time. What should any good theory be able to describe about dark energy, about the cosmological, about this astrophysical data? So here's at z equal to 0, a good theory should be able to describe the energy density here of dark energy. It has a value of about 5.3 by 10 to the minus 10 joules per meter cubed. This is from the lambda CDM model for the Planck collaboration. A good theory should also be able to describe the ratio of dark energy mass fraction to the baryons. A third thing that a good theory should be able to describe is this acceleration here, which is believed to be due to the cosmological constant. This has an equation, a state W, i.e. the pressure over the energy density, of -1. So this is just representative of an acceleration. And the other thing a good theory should be able, the fourth thing a good theory should be able to describe is the fact that the crossover from a decelerated region to an accelerated region occurs at a z of around about 0.8. Where did this model that I'm about to describe come from? Well, I was listening to a lecture by Professor Alan Guth in 2013, and he mentioned the dark energy, or Einstein's cosmological constant, was thought to arise from vacuum fluctuations of space. In other words, it was due to something called the Casimir effect, except that the high energy physics estimate for this Casimir effect was calculated to be a factor of 10 to the power of 120 times too large. And during this lecture, I thought, oh, well, I'm an expert in the Casimir effect. Let me go and see if I can explain this factor of 10 to the factor of power of 120. So I'm actually a soft matter physicist, and so I calculate the Casimir effect as part of my research. So let me explain the surface Casimir effect. In the surface Casimir effect, one has basically two perfect conductors, and then you have quantum, you have vacuum fluctuations, and they create standing waves between these perfect conductors. And of course, the electric field at the boundary must be 0. So here's the lowest energy mode. It has an energy of h bar omega, half h bar omega. Here's the next fluctuation which is possible. It has a shorter wavelength, higher frequency. Again, it has some energy, half h bar omega. What I knew from my research is actually for real materials, the dielectric constant of any material goes to 1 at ultraviolet frequencies. In other words, these boundaries disappear, and so this addition of these half h bar omegas gets cut off at about ultraviolet frequencies. Very, very recently, I had been had learned about something called the Casimir self-energy. In other words, you have a perfectly conducting spherical ball, because I was dealing with nanoparticles at the time, and you put the electric field 0 on the boundary, so you have waves going away from this ball, but you must cut off the counting of these, the contributions at ultraviolet frequencies. Okay, just like for the Casimir surface effect. So let's go back to what we're trying to explain here. At z equal to 0, of course, the dark energy energy density has this value here of 5.3 by 10 to the minus 10 joules per meter cubed. Of course, when we think about intergalactic space, we go down to here, the number of baryons, i.e. the number of protons, electrons, etc. in intergalactic space. We have about 1 baryon per 4 meters cubed. So here's my picture of what intergalactic space basically is. We have a box of sides 1.6 meters on each side, and inside that box, you either have a hydrogen atom or you have an ionized hydrogen atom, and the ionization fraction is nu E, okay? And so if the atom happens to be unionized, it has a Casimir self-energy given by this value, which you can just find in a book. Or if that hydrogen atom happens to be ionized into a proton and electron, then of course you have an electric field associated with that around the proton and electron. It's called the Born self-energy, and you just look up this. It has this value here. You can just find this in Feynman Lectures in Physics, Volume 2. In other words, if you know the radius of the proton and radius of the electron, you can find the Born energy. So let's go and do this calculation here for the energy density. Here's the calculation. I come along, I take the Casimir energy for hydrogen, and I multiply by the fraction of hydrogen atoms, 1 plus nu, inside this box. And then I add on to this the energy due to either a proton or electron times its ionization fraction, i.e. nu e, where nu e is given by the value which is measured by X-ray absorption in intergalactic space. The nu e has a value of about 0.4, 0.5. So this is an energy here, and then we've got to divide it by the volume of the box, 1.6 meters cubed. This quantity here is dominated by the Born self-energy for the electron, because the electron radius is so small, so this is given by that. So all we need to calculate this is the radius of the electron. So what you do is you try and find the best estimates. The best estimates come from electron-positron collisions, and the electron radius is about 2 by 10 to the minus 20 meters. So you put that in this formula and you get this value. And you go and compare this value to the value from the Planck collaboration, and you say, oh, hey, look, these values not only agree in magnitude, but they quantitatively agree. Okay, the next thing one would like to explain is the ratio at z equal to 0 of dark energy compared to baryons, i.e. the ordinary matter in my box. So we take the ratio of these two numbers, and the ratio of those two numbers is about 14.1. And then we compare that with my model. My model would say, okay, the dark energy should be the Born energy mass, so we're dividing by c squared, and then we divide by the mass of the proton plus the mass of the electron. Oh, we get about 19 plus or minus 6. Oh, these two numbers agree. So that's nice. One thing which is sort of peculiar about this model, of course, is if we go and calculate the mass, the Born mass, due to the energy in the electric field which surrounds the electron, we get a very, very high Born mass. It's about 7 by 10 to the minus 26 kilograms. In other words, it's 40 times as massive as a proton and 80,000 times as massive as an electron. And of course, this is the reason why dark energy, or the cosmological constant, dominates today, is because this Born mass is so very large. But of course, it's hard to get your head around this figure because it's so large. So the third thing we would like to describe is the equation of state, which has a value of -1. So the way you do that in this model is, well, we have an electron here, which is some distance x away from a perfectly conducting wall. And then you go to Jackson, and you look up Jackson, and you say, okay, you could replicate this situation of this perfectly conducting wall by putting an image charge plus q at a distance x to the right of the wall. And you look at the interaction of the charge and the image charge, and then you can throw away the wall. So that would allow you to calculate the force between the charge and the image charge. And then you say, where's the force greatest? Well, the force is greatest at the point of contact here. And then you divide it by unit area. So that would give you the pressure. And then similarly, you could go and calculate the energy density. And all of this is done in this paper here in Astrophysics Space Science. And you find that the equation of state is -1 for this model. Of course, we have some issues here in this model because in quantum electrodynamics, the electron is a point particle. And to get rid of this point particle, they have to go and do something called mass renormalization. So, you know, we don't want to change anything in QED because, of course, QED is the most accurate theory in physics. And if we change something, that would be problematic. So let's see what happens in QED. What happens in QED is we basically have a bare mass, MB. This comes from the Dirac equation. And then this bare mass gets dressed. In other words, here's some Feynman diagrams. So we can either have an electron traveling through space here along a direct path, or it can be dressed. It can come along and it can emit a photon which gets reabsorbed, or there can be more complicated corrections to this. So this quantum mechanical self-energy goes as some log RE, where RE is the radius of this object. And what happens in QED is these two contributions get mass renormalized. In other words, they get replaced by the mass of the electron times c squared. And where is our Born self-energy? Well, actually, that is assumed to be contained within this ME. So that's what happens in QED. One problem with mass renormalization that not many people realize, although Feynman realized it in his lectures in physics, volume 2, and that is that energy is not conserved. So what we would like to do is what we do in our model is we take out that Born self-energy from the ME, and actually that gets us back energy conservation. So that's a nice feature. So let's go and look at electron-positron interaction. It has this energy. So what we've done is we've taken the two contributions here, the bare mass, the quantum mechanical self-energy, and we've extracted also out the Born energy out, and then we've got to put in an interaction energy between the electron and positron. So this is from the Coulomb interaction here. So this is the energy between an electron and a positron. They're static, they're not moving, so there's no kinetic energy. Let's have a look what happens when we come along and do annihilation. So during annihilation, what we do is we put R equal to RE here. So, oh, that's nice. When we do that, that gets rid of all the electric field terms. So they just disappear, right? They just cancel out. And then we're left with this quantity here, which we come along and we put that equal to MEC squared. Oh, we've just reproduced QED mass renormalization when we do this. So in other words, by doing this, nothing in QED is going to change. We've just reproduced mass renormalization for QED. The other thing we can do in this formula here is, let's go back, is we can look at what happens if we have a free electron or a free proton. A free electron or free positron. We put R going to infinity when it is free. So here it is on the bottom line here. And actually by retaining the Born self-energy, we get back energy conservation. That's good, because actually what happens is that the work done against the Coulomb interaction, that's what gives us back this Born self-energy. So we get energy conservation back by retaining the Born self-energy. Let's look at the last thing that we'd like to explain, and that is this acceleration-deceleration transition, which occurs at about a z of about 0.8. if we go to the Friedmann equation, here's the Friedmann equation, and this this pi is given by basically the pi OM, that's ordinary matter, and this other term pi m dm is from dark matter, and then we've got some sort of cosmological constant here, or and of course, in our model, what we do is we get rid of that, and we've replaced it by the Born energy here. We can come along and rearrange these two equations here to get the nu E as a function of Z and find out whether that varies in a sensible manner. So all I've done is I've just rearranged that and got nu E as a function of Z. So we can actually calculate the nu E and say, okay, does this behave in a reasonable manner by taking these symbols. The symbols are the Hubble parameters, and we go and subtract off from this in this bracket here the value due to ordinary matter, the value due to dark matter, and so that allows us to do this calculation. When we do this calculation, here is what we find. Here is nu E as a function of Z going away, and the value at Z equal to 0, that's 0.4, 0.5. That's the value that we used in calculating our dark energy density. Where does this variation in nu E occur from? Okay, so from astrophysical data, this variation in nu E comes from something called WIM, which is a warm hot intergalactic medium. So what we have actually is we have low density voids in intergalactic space, and this hydrogen gas here flows into cosmic filamentary structures here. And these cosmic filamentary structures, they have a higher density by a factor of about 5 to 200, and the hydrogen gas which is flowing in, that gets ionized at a temperature of 10 to the 5 to 10 to the 7 K. So that's where this variation in nu E comes from. Of course, this is plotted as a function of Z. We can change the Z to a function of time. So that's what we've done here. We've taken that same data, nu E, and we plotted it as a function of time here. And let's look at our model. Our model, here's our Friedmann equation, but the nu E varies with time. So let's give it some time dependence. We think of it as a t to the power of s, where s is some value. And this differential equation here, we can easily solve that. So the time dependence of at goes as t to the power of 2 plus s over 3. Of course, we want an accelerating universe. So all we do is we differentiate the at twice, and we put that greater than 0, so for an accelerating universe. In other words, s must be greater than 1. So on this log-log plot here, we put a slope of 1. So anything with a slope greater than 1 is accelerating. In other words, from this graph, we can see that for any data where Z is less than 0.79, then it must be accelerating. From the previous study of Farouk in 2017, from Hubble parameter data, they found a Z of about 0.84. So again, we can explain that. In our model, we've basically explained dark energy arises from WIM electrons at temperatures of 10 to the 5 to 10 to the 7 K. Of course, our model also includes a candidate for dark matter. Dark matter in our model would come from cold electrons, perhaps created during the cosmic reionization of intergalactic space at a Z of 6 to 15. So we can use our model to come along and calculate the fraction due to dark matter. So we would use the same expression, but apply that for dark matter, and calculate this nu E for dark matter. and we get this expression here. In other words, here's what our model would say would be for the ionization of intergalactic space. We have a contribution from dark matter, right, of 0.127. This gives rise to dark matter. And then this B to the TS, this gives rise to dark energy when S is greater than 1. So here's a summary of our theory. The Born self-energy arises from WIM electrons at temperatures of 10 to the 5 to 10 to the 7 K. And this describes the dark energy magnitude today. The dark energy to mass, ordinary mass ratio has an equation stated -1, has acceleration, deceleration transition of about 0.8. Inclusion of the Born self-energy for the electron ensures that the total energy is conserved. ME couples to the electric and magnetic fields, whereas the Mg, due to the gravitational field, which is Me plus the Born mass, that couples to the gravitational field. And then we also have a potential candidate. The dark matter arises from cold electrons, the Born self-energy of cold electrons in intergalactic space. Okay, thank you. Goodbye. Okay, stop.